Hello everyone. Quantum mechanics describes many unusual phenomena, but Richard Feynman declared that it contains only one mystery. He said it in reference to the double slit experiment, and it's worth asking, why did he think so? In our opinion, Feynman wanted to suggest that each and every phenomenon is only non-classical if it expresses the signature of quantum superposition. When we study microscopic events, we encounter many classical and many non-classical properties. Surprisingly, the non-classical features turn out to be reducible in one way or another to the problem of superposition. For example, the process of entanglement is very different from double-slit interference. It seems to reveal a new phenomenon. Measurement A interacts with measurement B. But when we look at the relevant equations, it turns out that they are derived from something else. Population A is in a state of quantum superposition. Population B is in a similar state of superposition, and this is enough to derive extraordinary correlations between measurements. In what follows, we are going to argue that entanglement is just a complex manifestation of superposition. The appearance of measurement interaction is epiphenomenal. Quantum mechanics appears to imply the collapse of classical mechanics. One of the reasons to believe so is the ability of quantum states to violate the famous inequality of John Bell. This instrument works like a flower sieve. Both quantum and classical predictions may enter the realm of its solutions, but only quantum predictions may escape it. Presumably, the only way to violate Bell's inequality is by virtue of non-local interaction. Accordingly, Bell's inequality is a reliable test of locality. Or is it? A recent paper by Andrei Hrenikov raised a very interesting question. Bell's inequality belongs to a class of expressions in probability theory that were discovered long before the establishment of quantum mechanics. Some of these relationships were derived by Boole and are known as compatibility tests. More importantly, these tests were used for the study of classical phenomena. So, why is it that these inequalities can work as tests of compatibility everywhere else, but not in quantum mechanics? In order to answer this question, we need to learn more about this concept. When we have a mixed population, we expect that the net distribution of properties A and B is going to be compatible with the component distributions. It should be possible to prove mathematically that any sample of the mixed population is reducible to a mixture of the two isolated populations. If that is not the case, then we are dealing with mistaken assumptions about the components, or some sort of interaction took place. How do these tests work? Bell's inequality and its cousins are based on a very simple principle. Just because a process is governed by chance, it does not mean that anything is possible. Some combinations of properties are logically impossible. Hence, a test of compatibility is just a method of determining the limit of possible combinations in the absence of interference. For example, let us assume that we have a box with 26 balls. Half of them are black and the other half is white. At the same time, every ball has a letter of the alphabet on it. Let us assume that 6 balls are marked with vowel symbols and the remaining 20 are marked with consonant symbols. There are many different ways to mix colors and letters. In some configurations, the vowels can be evenly distributed between the colors, but in others, all of them can be found on objects with the same color. On the other hand, it is logically impossible to have all the white balls marked with vowels. There are 13 balls of one color, but only 6 possible vowel signs. To keep things simple, we can express the coincidence rate of two properties as a coefficient of correlation. This way, we can explain the nature of compatibility with minimal calculations. In this case, if we do our measurements and we happen to get a correlation coefficient greater than minus 0.08, then something is wrong. This can only happen if there are more than 6 balls with vowels on them. Therefore, our result would be incompatible with the known distribution of properties. Somebody or something had to interfere with our starting distribution. Let us examine this relationship with a more complicated example. Suppose that we have a source of entangled photon pairs, but these photons obey the laws of classical physics and never engage in non-local interactions. Let us also assume that each pair of photons can only have one of two states of polarization at the source, vertical or horizontal. In the right arm of our setup, we have a polarizing beam splitter with a fast axis in the diagonal direction. In the left arm, we have another PBS, but this one is oriented at 22.5 degrees from the horizontal plane. The question is, how does the property of passing through the diagonal channel correlate with the property of passing through the opposite channel? First, we do the analysis for the vertical polarizations. If we use the same rule that we described in the previous example, we get a maximal correlation coefficient of minus zero point 0.4. This limit is very low because a very small proportion of photons is transmitted in the left arm. Also, this is the maximal value of the correlation. We can only expect to see it when all the photons from this group coincide with the photons from this group and never with this group. For that to happen, we have to assume the existence of hidden variables enforcing the highest possible rates of coincidence. Still, hidden variables can only raise the coefficient to the maximal level. It is logically and physically impossible for them to break this limit. The same analysis applies to the two populations of photons with horizontal polarization at emission. This time, we notice that more photons will be transmitted by PBS1 than PBS2. This means that all the photons at plus 45 can coincide with photons at plus 22.5. Again, if we allow for hidden variables, the maximal level of correlation is 1. If we assume that every sample has an equal number of vertical and horizontal photons, we obtain the final prediction by taking the average of the individual coefficients. The physical justification for this is that photons with horizontal polarization are never expected to coincide with photons that have vertical polarization. In this way, we obtain a final coefficient of correlation of 0.3 for the mixed population. This is equivalent to the ceiling that would be imposed by Bell's inequality, except we used simplified calculations. What happens if we allow the two populations of photons to interfere locally in each path? The linear superposition of a vertically polarized beam with a horizontally polarized beam can produce a net state that is linearly polarized in the diagonal plane. Accordingly, 100% of all the photons will be transmitted in the right arm. For the same reason, 85% of all the photons will be transmitted in the left arm. As a result, we can predict a maximal coefficient of correlation of 0.7. The interesting part is that we do not have any element of randomness in this case, because 100% of the photons are transmitted by PBS2. Therefore, this is not just the highest value of the coefficient, it is the only value. We expect it to happen every time, without any hidden variables. To sum up, the highest conceivable level of correlation without interference is 0.3. The exact level of correlation with constructive interference is 0.7. This coefficient is definitely incompatible with the input distribution. 0.7 is much higher than 0.3. Yet we obtained this value without any sort of non-classical interaction between the measurements. This means that classical interference violates Bell's inequality. Now you might ask, what is the highest possible correlation in the quantum case? Surprisingly, linear quantum superposition predicts the same level of correlation as linear classical superposition, which is 0.7. From a quantitative point of view, classical interference is identical to quantum interference. Here is an explanation of this statement. Suppose that we have a rope which can oscillate in the vertical plane or the horizontal plane. Quantum mechanics tells us that when we have uncertainty, the rope oscillates in both directions at the same time. Of course, this is impossible in a classical context. A Newtonian rope cannot oscillate in two directions at the same time. However, classical objects do not violate the principle of momentum conservation either. So when the rope is excited in two incompatible directions, it has to oscillate in the net direction. According to the classical principle of linear superposition, the amplitude of the net state is equal to the local vector sum of the input amplitudes. Yet only the net state can be real in a classical context because a single Newtonian body cannot move in two directions at the same time. According to the quantum principle of superposition, the same relationship applies. We simply assume that states A and B are simultaneously real instead of state C. In terms of measurement outcomes, both approaches entail the same predictions. In short, quantum interference is formally identical to classical interference. What makes it non-classical is an interpretive element. We either know or assume that classical interference is impossible when measurement outcomes betray the effect of superposition. The difference between the classical case and the quantum case cannot be found in measurement outcomes or in the details of the math. It is found in the qualitative details that we attribute to the experimental context. The high level of correlation follows from the fact that we have two identical processes of interference going on, here and here. For this reason, we need to determine the composition of the beam prior to measurement. Do we have well-defined quanta in the net state, like a rope oscillating in the diagonal plane, or do we have undefined quanta that occupy several component states, like a non-classical rope that can oscillate in two directions at the same time? Let us begin by analyzing the classical superposition of incompatible states of polarization. When we are dealing with a classical continuous beam, horizontal components are split 50-50 by diagonal beam splitters if vertical components are blocked. The distribution is also 50-50 for vertical components if the horizontal beam is blocked. In contrast, superposition produces a different outcome. The net state is diagonally polarized and all the light from both components is transmitted. Nothing is reflected. This is a typical case of interference in perfect agreement with classical mechanics. The net diagonal state emerges because vertical and horizontal components overlap with each other in phase continuously. Let us now introduce an attenuator in the path of the input beam so that the total intensity is low enough to generate discrete detection events. We have entered the quantum regime, but radiation levels are still high enough to allow for classical overlap between photons with different states. We have the appearance of quantum interference, but the difficulty is to explain what this means. Can we declare that classical mechanics has failed just because the pattern of detection is discrete? The answer is negative. Quantum superposition is not necessarily real if classical superposition is also possible. What if we now attenuate the source of photons to the lowest possible levels of detection? Indivisible photons are now expected to emerge one at a time, and by classical principles, they can only take one of two paths. Accordingly, we expect loss of classical interference, and the prediction for the final distribution is 50-50. Isn't this a good way to test the reality of self-interference? Unfortunately, non-classical models predict the same thing. At extremely low levels of radiation, we find that coherence is lost or other uncertainties pop out, and interference is no longer visible. As a result, both theories end up with the same prediction, and we are still unable to tell which interpretation is correct. In practice, quantum predictions are separated from classical predictions by performing experiments at intermediate intensity levels. The rate of emission is chosen to be high enough to preserve quantum indistinguishability, but low enough to exclude classical overlap. The crucial assumption here is that overlap and indistinguishability are not the same thing. It should be possible to achieve indistinguishable photons even when their physical overlap is impossible. This, of course, raises the question: how can we tell the difference between classical overlap and quantum indistinguishability if we cannot observe the photons directly? The answer is that we have to take the clues that are available and supplement them with reasonable assumptions. Indeed, we find on closer inspection that non-classical interpretations require the reality of the following four conditions. Photons have to be indivisible, point-like particles that are perfectly detectable and never interact with each other. If all of these assumptions are adopted at the same time, then it seems natural to conclude that classical mechanics fails. Yet these are not the only reasonable assumptions. If we make alternative postulates, then the same outcomes are compatible with classical superposition. In short, both interpretations are compatible with existing observations. It is not necessarily true that the principles of classical mechanics have failed at the quantum level. As pointed out by Richard Feynman, superposition is the only mystery in quantum mechanics. Yet we have shown that classical superposition and quantum superposition are formally identical. We can only rule out one of them on the basis of unverifiable assumptions. Therefore, Bell's inequality is just a test of interference. In terms of probabilistic analysis, it is a test of compatibility, just like the Boolean inequalities of the 19th century.